Now I'll tell you a little story that actually Professor Wojciech played an important role in launching the Ricci flow, which came about in the following way. In the first half of the 70s, I was trying to prove a version I conjectured that would be a much nicer version of the Nash-Moser inverse function theorem. But I was totally stuck on it, but I kind of vowed to keep working through eternity, sort of like the Flying Dutchman. And then I was talking to Louis Nierenberg one day, and he said, well, I think that there's a counterexample by Wojciech. And I checked it out, and there was. So I then, despaired of trying to prove this big result on the Nash-Moser theorem, and decided to do something different. And that was when I started working on the Ricci flow. So if it hadn't been for Professor Wojciech, I might still be trying to do something that wasn't true. So the idea for the Ricci flow came about because my first job was at Cornell University. I had been hired by Jim Eales. And he and Joe Sampson had just done the harmonic map heat flow from a map of one manifold to another. And the idea there was that was the first really good example we had of solving a nonlinear parabolic system. It's like diffusion, like a heat equation, to take a very rough map and straighten it out to something very regular. In this case, something that was analogous to solving Laplace's equation. So I thought, well, if we can do this for maps, why can't we do it for other geometric structures? And the most basic structure in differential geometry is the metric. So I thought, okay, let's take a metric and try to spread it around evenly by some kind of heat equation. Heat tends to distribute equally over a body to make it a very nice metric. In particular, hopefully, a constant curvature metric. And that was when I wrote down the Ricci flow. So it really is sort of like if you know any Riemannian geometry, if a manifold has zero or constant Ricci curvature, that's really analogous to Laplace's equation. And in Einstein, in general relativity, said, well, let's try to figure out how we can make the metric correspond to the gravitational field. And he wanted it to coincide with Newton's theory in the case of a weak gravitational field. So he said, okay, then you have a harmonic potential, that the Laplace of the potential is zero. So what would it mean to say that the Laplace of the metric is zero? And he decided that was Ricci was zero. But in the case of space-time, what you have is a Lorentz metric. So there, instead of a Laplace equation, it's a wave equation. So that's the wave equation for a metric. And the Ricci flow here is just the heat equation for a metric. So now we get to see if the projector works. Okay. So I'd like to introduce you here to Muffin. Muffin is my computer. And I use her to do a whole lot of mathematics, both for writing articles, but more especially for doing algebraic computation and simple numerical simulation. So she's going to show us some movies today, but since I'm still sort of an amateur at this, I was just being given a lesson on how to export movie files. But she might actually get brain freeze at some point in the lecture. I think she gets a bit embarrassed with a big audience. So if you'll bear with me, if she should freeze up, I'll just have to take a minute and restart her and give her some encouragement. Anyway, let me give you a brief introduction to the basic ideas of Riemannian geometry. And you don't actually have to know a lot of geometry to do Ricci, but it's mostly just a little bit of language. So what is a Riemannian metric? It's actually a positive quadratic function on the tangent vectors. And so the metric on a tangent vector gives you the length squared of the vector. I write the metric as little g, so that's what it looks like on Euclidean space. That's the Euclidean metric. So you may be familiar with the metric as a symmetric bilinear form, and of course there's a complete correspondence between quadratic functions and symmetric bilinear forms. And the symmetric bilinear form really corresponds to a dot product. So that means we have lengths of vectors and angles between them in a way that looks at a point or near a point very much like Euclidean space, but over large distances can vary. And you can then define the length of a path simply by integrating the length of the tangent vector. And shortest paths between 2 points are called geodesics. And here's a picture of a surface. This is actually a piece of a quotient of the hyperbolic plane. It has constant negative curvature, and the red curve is showing you the shortest curve from one point to another. And now the nice thing about being an interactive file is I can rotate the picture around and show it to you from different points of view, like that. The next invariant that you get out of the metric is you get a notion of parallel translation, which basically tells us how to translate a vector around the path without having its direction change infinitesimally locally as much as you can. So, for example, if you have a surface in Euclidean space, as you move, you take a tangent vector that's initially tangent. If you were just to parallel translate it in the Euclidean sense, it wouldn't be tangent anymore. You have to move it somehow, and the least you can move to make it keep it tangent is just to move it in the normal direction. So if you always adjust it in the normal direction to keep it tangent, you get this parallel translation for a surface in space. Now, when you're dealing with a Riemannian metric in the abstract, it's not something embedded in the Euclidean space in a specific way. It's totally intrinsic. So like for the physicist, Einstein says our universe is not flat, it's curved. But as far as we know, we don't know anything bigger that it's curved in. It's just curved in itself. And that's the sort of intrinsic geometry that we do here. So here's an example of parallel translating a vector around a curve. And what you see is that if you go all the way around a curve, that you start in one direction and you come back in another. And that twisting is called the holonomy around the path. So it turns out that the holonomy is generated pointwise by a tensor called the curvature. And then the actual holonomy, the turning, when you go all around a curve, is more or less, it's true in 2 dimensions, an integral of the curvature over a surface bounding path. So, in general, the curvature tensor is something that gets applied to 4 tangent vectors. And that's an awful lot of vectors. Okay? But Riemann of x, y, u, v says if you were to parallel translate around a little infinitesimal parallelogram spanned by the tangent vectors x and y, it tells you how much u would rotate in the direction of v. Okay? So that's why you need 4. Well, it's kind of hard to understand something that, and it has a lot of nice symmetries. But there's one way is that if you think of the x and the y, it's antisymmetric in the x and the y, and it's antisymmetric in the u and v. And so it's really a quadratic function on the 2 forms. And if you have the vectors x and y, and you think of x wedge y as the 2 form or the little infinitesimal area element of the span of the parallelogram spanned by x and y, then the Riemann is a quadratic function on that 2 form, just by giving Riemann of xy, xy. If x and y are orthogonal unit vectors for a tangent plane, then that gives you the sectional curvature of the tangent plane. So, since that's so complicated, there's actually a trace called the Ricci curvature, in which you simply take, to do the Ricci curvature is a quadratic function on tangent vectors, and if you take a tangent vector and then take a collection of mutually orthogonal frames through that tangent vector and sum up, the sum of those curvatures is the Ricci curvature of the direction of the vector. And if you were to sum over all a mutually orthogonal set of tangent planes, not all through one vector, just all of them, then you just get a number, which is the scalar curvature at the point. Okay? So we have the Riemann curvature, the Ricci curvature, and the scalar curvature. Now, as I said, the Ricci curvature of the metric is really analogous to the Laplacian of the metric. Okay. So now how do I write down the heat equation for a metric? It's supposed to be ddt of the metric is the Laplace of the metric. So it's ddt of the metric is the Ricci curvature. Only there's a minus sign and a factor of 2. Factor of 2 is cosmetic. It's just so I don't get a half later. The minus sign is very important because, as you know, the heat equation only goes one way. It doesn't work backwards. Okay. And it really is minus twice the Ricci curvature that's the analogous thing to the Laplace of the metric. You don't see it in Einstein's equation because if you set that equal to 0, then it doesn't matter. And in fact, when I first tried the Ricci flow, I didn't have the minus sign, I didn't have the 2. I'd fix it up later. This was also discovered by Dan Friedan doing string theory. In 1986, he published a paper in which he derives the Ricci flow as the one-loop approximation for the renormalization group. I've learned to say the words. And actually, if you look at his equation, it's going backwards too. And the physicists string theory people want to do it that way. That actually they think that somehow ancient solutions of the Ricci flow, those that are coming from time minus infinity, are somehow supposed to correspond to the actual renormalization group, or so have been told. Don't ask me to tell you any more about it. So anyway, since it's a parabolic equation, we want to look at the initial value problem. So we take an initial metric, and then we proceed to solve over time and see how the metric evolves. And then we hope that it's going to spread the metric out evenly over the manifold. Let's see an example of this happening. So this is an example on the doughnut, which formally is, of course, called the torus, but just think of a donut. Now, the thing about this donut is that it's going to end up with a flat metric. If the donut that you eat does not have a flat metric. Okay. However, a cylinder has a flat metric. The cylinder looks curved, but that's its curvature in the ambient space. Its intrinsic curvature is 0. I didn't have a piece of paper. I was going to do the thing of folding the paper around it. And yeah. Good, perfect. So this is a Riemannian manifold with intrinsic curvature 0. If I bend it in space, it has extrinsic curvature in the space, but its intrinsic curvature is still 0. If you were a two-dimensional being and you lived on this piece of paper, you wouldn't know that it was curved. It looked as flat. all your theorems of Euclidean geometry would still be true. And I could roll this up as a cylinder like this, and it still has zero curvature. And now if I could actually roll this end into that end, then I'd have a donut with zero curvature. Only I'd need an extra dimension to do that, which I don't have. So what I show you is a donut, and it's isometrically embedded because Muffin actually has taken the trouble to calculate, first of all, numerically the solution and then numerically the isometric embedding. But you have to imagine now that the left-hand end is identified with the right-hand end. And if you do that, then that's exactly the metric, and this is what happens under the Ricci flow. As you see, it's straightening itself out, like that. And if you wait a while, it actually gets fairly straight. You'd have to wait for an infinite amount of time to have it actually be exactly straight. Good. So now, let me point out that if you're in this region out here, where it's curving the same direction in space in two different directions, this is positive curvature, like a sphere. In this region in here, where it curves, this curve goes this way and that one goes that way, that's negative curvature. That's like a saddle. And so, where the curvature is negative, minus the curvature is positive, and it gets bigger. The metric gets bigger. Whereas in this region, where the curvature is positive, minus it is negative, and the curvature gets smaller. So when I run it here, you see it's getting bigger here in the middle and smaller there, and that's how it straightens itself out. Okay. Like that. Thank you. So now, we'll move on a bit. So I'm going to overview some general principles for the Ricci flow. And the first one is dilations. That typically any partial differential equation may have a group of symmetries. And that the more symmetries it has, the nicer an equation it is. So one symmetry this equation has is dilating. But if you dilate space, then you have to dilate time like space squared. That would be true just of the heat equation. du dt is d squared u dx squared. Because you're equating one time derivative to two space derivatives. And if you do that, if you take a solution to the Ricci flow, dilate space and time, you get another solution to the Ricci flow. Now, any time that you have a symmetry for a PDE, you can get a solution that moves by the symmetry. So in this case, I have a very simple solution to the Ricci flow that moves by dilation. Namely, if I start on the sphere, well, the sphere looks completely the same everywhere. So it's got to keep looking completely the same everywhere, but it has positive curvature, so it will shrink. And the smaller it gets, the bigger the curvature and the faster it shrinks. So you see here, it's shrinking really fast, and faster, and pretty soon, poof, nothing's left. We'll come to that towards the end. That's called finite time extinction. Okay? We end up with nothing in the finite time. Now, it's also true that if you have a metric of constant negative curvature, which you can do on a donut with multiple holes, then that constant negative curvature metric will have a solution that simply dilates by expanding. And I'd show you that movie, but Muffin was having trouble making a donut with two holes. but you can easily imagine it. Now, it's also true that this flow has an infinite dimensional symmetry group, because there's the group of diffeomorphisms, which means you move the manifold around in itself any way you like, as long as it's nice and smooth and invertible. And so, since the diffeomorphisms are, as you take a metric, solve the Ricci flow, and do a diffeomorphism, it's the same as if you do the diffeomorphism and then solve the Ricci flow. So, you can then get solutions that move only by a diffeomorphism. And that means that basically the metric is always the same, but where the metric occurs on the manifold changes. So here you will see a solution which I've named the cigar. The string theory people call it Witten's black hole. It doesn't look like a black hole to me. I called it the cigar because I drew the thing and I wanted to remind myself it went on to infinity, so I had some wiggly lines at the end, and it looked like smoke coming out the end of a cigar. And no, kiddies, I do not recommend you smoke. I don't smoke myself. But anyway, what I've done is I've colored the different bands here so that you can see that the metric is moving. And in fact, the curvature here is positive everywhere, so the metric's always shrinking. In spite of the fact it's always shrinking, the shape doesn't change. It doesn't get any smaller. How can it keep shrinking and not get any smaller? It's infinite. Half of infinity is still infinity. Okay. So that's an example of a soliton that moves by a diffeomorphism. We also have expanding and shrinking solitons that move by a diffeomorphism and expand or shrink at the same time. Then there are isometries. So if your metric has an isometry, that's a motion of the manifold to itself that leaves the metric unchanged, then that group of isometries is preserved. So, for example, if you just picture a round donut, you can rotate it around. Okay. Well, one way that you get a metric on a manifold with a lot of isometries, if it's a metric on a Lie group, and you take, say, a left invariant metric. So S3 is a Lie group. Let's look at some metrics on that Lie group where they're invariant under the left action of the Lie group. So S3 is a three-dimensional manifold that, just like S2 is all the points in a three-dimensional space at distance 1 from the origin. S3 is all the points in a four-dimensional space at distance 1 from the origin. And now if you can't really picture S3, that's okay, I can't either, but we learn to pretend, and so you kind of visualize. And the isometries are generated by the three rotations as vector fields. It has a nice simple Lie algebra, and from that you can do computations. So I take a homogeneous metric where I specify that A, B, and C are all perpendicular to each other, but I can specify their lengths. And in this case, I specify the length squared to be P, Q, and R, because the metric measures a length squared. And then what you find is the Ricci flow just turns into a simultaneous system of three ordinary differential equations and the three unknown functions, P, Q, and R. And the square roots of those are the actual lengths. And so I started with an example where A had length 4, B had length 2, and C had length 1. And that's given in red, yellow, and blue. And there you see the bottom axis is time, and the vertical axis is P, Q, and R. And you'll see that initially P always drops off, but initially Q and R grow. But Q grows quite a bit until it's equal to P, and then they both start coming down. And R grows a little bit, and then when P and Q catch up to R, then they stay pretty equal, and they all go down to 0. Remember, the curvature here is positive, so it keeps shrinking. Okay. Now, it was kind of hard for Muffin to make a movie of S3, so what I did was, I made an ellipsoid whose like 3 principal radii are the lengths of A, B, and C. And I think this corresponds to slicing like the circle where X is Y and Z is W, and then the circle where X is Z and Y is W, and the circle where X is W and Y is Z. And those would all be mutually perpendicular, and those correspond to the 3 principal circles around this ellipsoid. And so now you'll see this is the P and Q rapidly becoming equal, and then they're shrinking down until they get close to the R, and I do hope Muffin doesn't freeze it. Good girl. Good girl. Yay. Yay. You can do it. And then it turns into a nice round little sphere, which will then, of course, disappear in a finite time. Okay, so there's a nice example. So now, another case is a product. If you do the Ricci flow on a product of 2 metrics, it's just the product of the 2 Ricci flows. Each factor doesn't care what the other one does. Well, we have a nice long time existence theorem. Long time doesn't mean forever. But the idea of a long time existence theorem is that your solution exists up until some time, and you know why it's not going to go on any longer. So in this case, what we know is that a solution to the Ricci flow is going to exist until either it goes on forever, or it exists up to some finite time when the curvature is going to infinity. And when the curvature goes to infinity, obviously there's not a smooth solution. You might have some kind of weak solution, but you don't have a smooth one. We actually don't have a definition of a weak solution for the Ricci flow yet. At least not one that we can do anything with. Okay. Well, we also have formulas for the Ricci flow. So we know how the length evolves. The rate of change of the length of the curve is minus the integral of the Ricci in the tangent direction over the curve. And the rate at which volume changes is minus the integral of the scalar curvature. And we also have a nice formula for how the curvature evolves. And now, when I first started working on the Ricci flow, I didn't really know if it was going to do anything. But it was when I computed the evolution of the curvature and got something that looked very nice, very much like a diffusion reaction equation, just like an Neil Sampson. I said, okay, Peter, there ought to be some gold nuggets here, if not a whole mine. So ddt of the Riemannian curvature is the Laplacian of the Riemannian curvature in the metric. There's a good way to define that. Plus a sum of 2 terms, each of which is quadratic in the curvature. And the first is just a square as an operator, and the second is a square involving the Lie bracket. And the first square as an operator is that curvature makes the metric shrink, and shrinking makes the curvature bigger. That's where the square comes from. The Lie bracket one comes from the Holonoid. That if you have curvature around one plane, and it diffuses, the curvature in that plane diffuses around another plane, then you can actually generate curvature in a third plane. That's what that one's about. That's as good as I can explain. There's explicit formulas for them. We'll see in 2 and 3 dimensions later. Now, the Ricci curvature tends to like positive curvature. And so, in general, remember that the curvature can be regarded as a quadratic function on two forms. That's called positive curvature operator. And that is actually preserved by the Ricci flow in all dimensions. And in many cases, you'll find other notions of positive curvature are preserved. And often when the curvature isn't positive, it'll evolve to be positive, or at least less negative. Okay? So this equation likes positive curvature. There's also an interesting splitting result that is, for those of you who know a little bit of PDE, it's really equivalent to applying the strong maximum principle here, that if you have a metric where the curvature is weakly positive, and it's not strictly positive after you've waited any little bit of time, then anything that would be making it go positive has to be zero. And in the case where there's a zero in the Riemannian curvature, that means the holonomy is restricted. That you go around different paths and you can only do some things, not everything. And in the case where Ricci curvature is zero, it means it actually is splitting off as a product with a flat line in that direction. Okay. Let's see. I think I did long-time existence twice, so let's forget that. Okay, so now I said I was going to talk about the Ricci flow in low dimension. So in particular, I'm going to look at dimension 2 and 3. And on a surface, that's dimension 2, it's particularly easy because the Ricci curvature is just a half the scalar curvature times the metric. Well, why is that? The curvature, remember, is really a sectional curvature of a tangent plane. And on a surface, there's only one tangent plane. So there's only one curvature. Okay. So the equation's a bit simpler, and in particular, since the metric is changing by a function times the metric, that means that you're changing conformally. Conformally means angles are preserved. Okay? So in 2 dimensions, the conformal structure is preserved. And of course, Gauss-Bonnet tells you that the integral of the scalar curvature is a topological constant in terms of something called the Euler class. For a surface that looks like a multi-hole doughnut, it's the number of holes. Okay. Now remember that there's this evolution and diffusion reaction equation for the curvature where ddt of the curvature was Laplace of the curvature plus some quadratic terms of the curvature. Well, in 2 dimensions, it's just ddt of the scalar curvature is Laplace of scalar curvature plus scalar curvature squared. It's just about as simple as that simple diffusion reaction equation. I think there's a little catch here. It's a bit more nonlinear than it looks because the metric is changing by the curvature, and that changes the Laplace operator. So, okay, so it's a little subtle here. Now, soliton, remember, was something that moves by a diffeomorphism, and the only shrinking soliton is the round sphere, and the only steady soliton is the cigar that we already saw. But there's another interesting solution. It's an ancient solution, and it goes back to time minus infinity, and this was first found by J.R. King. And interestingly enough, it can be found in closed form. Now, a lot of physicists and engineers and undergraduate students love solving PDEs in closed form. And when you can do it, it's great, and you really understand that you've got a solution. However, I have to tell you, for if you're not experienced in it, that the chance of your PDE having a solution in a closed form is like epsilon to the 10th. Okay? So that kind of thing doesn't happen very often, but sometimes it does. And now, what does this solution look like? Well, it extends as far back in time as you want. And it actually looks like two cigars that, like on one end and the other, that the cigar ends in a cylinder, and you kind of hook one up to the other. So at a very early time, it looks like this, and that's a metric on S2. The curvature is positive, so it shrinks, but you notice that the real positive curvature is out here, and in this region, in the middle, it's nearly flat. So essentially, you're not going to see anything happen in the middle until these ends shrink it. And it just collapses up like that. Okay. And then, of course, once it's shrunk enough, it's looking spherical, and then it just shrinks down like a little sphere. And I stopped that one before it actually went away, but it would, of course. Okay. So, now let's come to some theorems. So we have a complete understanding of the Ricci flow on compact surfaces. And basically, you can divide into three cases where the Euler class is positive, zero, or negative. And the simplest case is where the Euler class is negative. That's like a surface of a donut with a lot of holes. And in that case, the solution will exist for all time, and it's just going to keep getting bigger and bigger without limit. As it gets bigger, the curvature is getting less, and it doesn't grow quite as fast. But what you'd like to do is make it converge. So if something's just growing and you want to make it converge, you want to scale it down. In this case, all you have to do is divide the metric by the elapsed time, and then you get a scaled down version that actually converges, and it converges to a metric of constant negative curvature in the conformal class. And let's see, I missed this one. Well, okay, when the Euler class is zero, you don't have to rescale. That's like the torus, at least. Or there's another one that's the Klein bottle. You've probably all seen a picture of the Klein bottle, which is this surface that's not orientable, and it kind of snakes back in through itself. Okay. And in that case, you don't have to normalize. The Ricci flow just goes to the flat metric in the same conformal class. In the case of positive Euler class, which means you're either on the sphere or the projective plane, you have to work harder to prove this theorem. And there's a number of ways of doing it, but one nice way is this isometric estimate. So you take any curve, you look at its length, and you look at the area it bounds on one side and the area it bounds on the other. And then you take length squared times 1 over the one area and 1 over the other area. And that's scale invariant. And then you take the infimum over all curves. And that's a nice isoperimetric estimate. So this isoperimetric quantity increases under the Ricci flow on a compact surface, well, on a sphere. Okay. So then you can do an analysis that will do at greater length than 3 dimensions, where you say, in this case, you want to prove there's no singularity. So you say, suppose a singularity formed, well, then I can do a blow-up argument, and I'd get a cigar. And then the cigar has this isoperimetric ratio 0. So you'd get a contradiction, because i's got to be bounded positive away from 0, since it's increasing. And proof in the general case, where the curvature can change sign, is due to my friend Ben Chow. And it's that if you take any initial metric on a compact surface with Euler class positive, sphere of the projective plane, the Ricci flow exists only up to a finite time when the diameter goes to 0. But if you rescale dividing by the time to the collapse, then you get a rescaled flow that converges to the constant positive sectional curvature metric in the conformal class. So you put all this together and you get a reproof of the classical uniformization theorem. So now I'm going to tell a little story about myself. That when I was first working on the Ricci flow, I was advised by a senior distinguished mathematician, said, well, why don't you start in 2 dimensions and try to reprove the uniformization theorem? And if you can't do that, you won't get anywhere. Well, I was young and arrogant, and I thought, no one will care if I reprove the uniformization theorem. Let's start in 3 dimensions, which turned out to be a lucky thing, because there's a theorem in 3 dimensions that's easier to prove than this result in 2 dimensions. I did the 3-dimensional case in 82, and I didn't get 2 dimensions till 86. So anyway, and why did I do 3 dimensions? Well, that's simply because, like I told you, I don't much like the Riemannian curvature tensor. It has too many vectors in it, too many indices, kind of like Mozart's music has too many notes. You remember the movie? Anyway, let's start by looking at 2 dimensions. And in 2 dimensions, you can recover the whole curvature tensor just from the Ricci curvature, or equivalently from the Einstein tensor, which you can define as half scalar times metric minus Ricci. Now, the idea in the Einstein tensor is, in 3 dimensions, if you take a vector, then there's a unique tangent plane perpendicular to it. And with the Einstein tensor, then the Einstein tensor is a quadratic function on vectors, and you apply it to a unit vector, and it gives you the sectional curvature of the orthogonal plane. So, the evolution of the Riemannian curvature turns into a diffusion reaction equation for the Einstein tensor, and that is the E dt is Laplace E plus twice times E squared plus E sharp. And in this case, you can represent E as a quadratic function or symmetric bilinear form. I can represent it as a matrix. I can always pick a frame where it's diagonal. And if you look at a frame where E is diagonal with eigenvalues lambda, mu, and nu, then E squared is lambda squared, nu, and E sharp is mu, nu, lambda, nu, and lambda, mu. So the E sharp is actually the adjoint matrix. And there's a maximum principle for systems that only works for equidiffusive systems, which means you have some different quantities, but they all diffuse by at the same rate. And that happens typically in a system where ddt of everything starts out as the same Laplace of the thing, plus the lower order terms. Okay? So in that case, what it says is that if you have a convex set, and if it's preserved by the reaction, which is what happens if you drop the diffusion and just look at the ODE system, you have a convex set that's preserved by the reaction, and it's also preserved by the diffusion reaction system. Okay? So the diffusion reaction system in this equation is these 3 ODEs in the 3 unknown functions of time, lambda, mu, and nu. So the first result you get is that in 3 dimensions, positive sectional curvature is preserved. And to see that, you just look at the reaction, and if lambda, mu, and nu are positive, then d lambda dt, d mu dt, and d nu dt are positive. So they all get bigger, they stay positive. Okay, and then you have to check out that that defines a convex set. Actually, check it's a convex set of matrices, but that's pretty easy. In a similar fashion, in 3 dimensions, you can show that positive Ricci curvature is preserved. And now, since the system of ODEs is homogeneous, they're all quadratic. Go back here they're all quadratic. Yeah, okay. So then what you can do is, for a quadratic system, you can project your vector field back onto a plane, say. And then you don't get exactly the same flow because the rate can change, but you get the same flow curves. So here I'm projecting back onto the plane lambda plus mu is 1. And in this case, instead of having 2 axes, you have 3 axes. So since lambda plus mu is 1, one of these lines represents, say, where lambda is 1 and mu and nu are 0, and so on. I think that one of them represents, say, where lambda is 0 and mu and nu is 1. And this one might represent where mu is 0 and lambda and nu are 1. And then this corner here is where lambda and mu are 0 and nu is 1. And it's like this, and this is where the center is where they're all a third. So these 3 vertices of this triangle correspond to having 1 positive curvature and 2 zero ones. That's like the sphere across the line, which is the cylinder. Okay? And in the cylinder, it's a product, so the sphere shrinks and the line stays the same. And so after you project, you just get a fixed point for your slope. And the center, of course, represents the 3 sphere, where they're all equal. And again, there they would all be growing, but when you project back to this plane, you just get a fixed point. So this is a nice, attracting fixed point at the middle for the S3. The S2 cross S1s are very degenerate fixed points. And it tends to come into them this way and this way, but then if you're in here, it comes out and goes into the center. And so here you see this triangle here being preserved, which is positive sectional curvature preserved. From the triangle, you always flow into the middle. And in fact, if you're not hung up on one of these corners, then it would all shrink into the middle. For positive Ricci curvature, it's this bigger circumscribed triangle like that would also all float in, which is why positive Ricci curvature is preserved. So then, in 3 dimensions, I proved this theorem. Did I miss it? Where did it go? Oh, I didn't get it in somehow. Oh, okay, here it is. So in 3 dimensions, this is what I proved back in 1982. If you start on a compact manifold and suppose the initial metric has strictly positive Ricci curvature, then the solution exists up to a finite time when the diameter goes to 0. And if you rescale by the time to the collapse, then it will actually converge to a round metric. And that proves the theorem that any compact 3 manifold that has any metric of positive Ricci curvature topologically is diffeomorphic either to the 3 sphere or a quotient of it by a group of linear isometries. Those are called space forms. There's a lot of interesting ones. Like you can quotient by something like the double cover of the dodecahedral group. Anyway, so the fun thing was that Yao and Ricci and a bunch of other fancy famous people were trying to prove this using minimal surfaces and made a lot of progress but couldn't quite do it. And then, kind of like when I did it, Yao actually is very, very pleased to know that he quickly embraced the Ricci flow and said, oh, this is great. So anyway, now let's go back to the more general case. Well, what you'll notice is that if you're out in this negative curvature region in the ODE, it's tending to want to come back to where the curvature is greater than or equal to 0. But you can be hanging up here on these cylinders. So there's a following theorem, which was first published by Tom Ivey, which is that if the initial metric is scaled to have all the sectional curvatures at most 1, but then subsequently, you get a bound that wherever the scalar curvature is bigger than 1, the minimum sectional curvature is on the order of minus r over log r. And now it's very important that you divide by log r, because if r is huge, log r is fairly big. Now, it's a very small effect that if r gets up to 10 to the 10th, then you got only about a tenth as much negative curvature. But in the limit, as the curvature goes to infinity, it says that the limit takes you into non-negative curvature. And that's very important for the subsequent analysis. Okay. So, now I get to talk about singularities. In dimension 3, where you're not restricting to positive Ricci curvature, you can get interesting singularities where the curvature goes to infinity, but the diameter hasn't gone to 0. That is, there's plenty left when the singularity forms. And there's a procedure for analyzing singularities. It was done in a lot of cases, in elliptic cases, like in minimal surface theory, where you have a singularity in a minimal surface and you do a blow-up arc. And then you get a radially invariant minimal surface. And then you can go out in spatial infinity and do a blow down and get a product of a line with a minimal surface of one lower dimension, and then proceed inductively. So I got nice tutoring in this from Rick, Shane, and Yao when they were with me in San Diego, and Wykład was there, and we proceeded to apply the same thing to the parabolic flows. He worked in mean curvature flow, I worked in Ricci flow. And the two cases are enormously similar. In fact, all the pictures look almost identical, and all the analysis is almost identical, except that in Ricci flow, it's always one dimension higher. Okay. So now, the simplest singularity that you encounter is the neck pinch. And it was all the way back in 82, right after I'd done the positive Ricci curvature case, that Yao came to me and said, look, if you don't have positive Ricci curvature, you're going to be pinching necks. And hey, guess what that's going to do? It's going to do this topological decomposition, breaking the manifold up as a connected sum, and then maybe you prove Poincare conjecture or geometrization conjecture. Okay, so we were thinking about this back in 82. So imagine that part of the manifold is close to a long cylinder where the spheres have a radius that's small compared to the length, but that the spheres in the middle are smaller than the ones to the outside. Then the little spheres will want to shrink, and they'll get even smaller, faster, and that'll cause a neck to pinch down. And you'll end up with one sphere shrinking to a point that becomes singular, and then you get horns on each side. So the term horn here was introduced by Perelman, but I like it. So here I have a model of S2 cross S1. But again, you have to imagine, since I want to isometrically embed it, that the left end and the right end are identified. But you have to further imagine that there's an extra dimension here, which is that you look at the S1s going around this surface, like, say, this S1 going around here, and you have to imagine that's really an S2. Okay? Can you do that? Okay. Yeah. Okay. So anyway, and then you're identifying this with this, and we're interested in this region in the middle, where the neck is going to pinch. So now notice this is a little S2 that has positive Riemannian curvature. It's going to shrink. The curvature in this direction, the Ricci curvature in this direction, is actually slightly negative. So the neck actually gets a little bit longer, but that's very small compared to how fast it's shrinking here. You might or might not see it here. So anyway, let's go, Muffin. Good girl. So you'll notice at first, it's not shrinking too fast, But then as that little neck in the middle gets smaller, it shrinks faster. And as it shrinks faster, it gets smaller, and pretty soon, it just collapses down to a point with two horns on either side. Okay? So this is the process by which the Ricci flow can break up a three-manifold according to a connected sum decomposition. However, now, what happens if you do the blow-up analysis I was talking about? Well, you go in here just before this neck collapses, and this region here looks very much like a cylinder. And so what you have to do is imagine that each solution to the Ricci flow is a movie. And if I dilate space and time like space squared, a dilated movie is another movie. It's a movie in slow motion in close-up. And then you dilate again, and you have slower motion and closer up focus. And you dilate an infinite sequence, and then you take a limit of movies, and it's another movie. And this movie will now go all the way back in time. And that's because initially you just have a finite time, but you keep dilating the time more and more, so the time it's been around goes to forever. And so dilating gives you an ancient solution. And then we have theorems that tell us that there aren't a lot of those. In fact, in dimension 3, we conjecture only a few that we know, but we can't quite prove it. That doesn't matter. We know a whole lot about what they have to look like. So this singularity we think is the only one that happens generically. But there's another singularity that can occur, which we call the degenerate neck pinch. And here, part all goes away. So this is still just a regular neck pinch. And here, now of course there's more to the manifold off to that side, but I'm only showing you the part that's interesting. Oh, Muffin. Sorry. So let me kind of let her calm down here a minute, and I'll chat with you. So, let's open up mathematically again. See, these movies have a lot of information in them. And now the thing is that I've opened it up, but it's going to take her a minute to actually get everything loaded up here. I have to not be too impatient with her. Okay. So what's going to happen in the degenerate neck pinch is that it's possible to pinch down a neck and you're left with something on each side, but one side might be only a little sphere, a little spherical bubble ending in a horn. Okay? And on the other hand, if the neck was a little bit wider and the spherical bubble a little bit smaller to start with, then as the neck pinches down, before it can pinch off, that spherical bubble will pull through, and you won't get any singularity at all. So in between pinching a neck with something on both sides and not pinching a neck at all, there has to be something in between by continuity. And that's the degenerate neck pinch, where the neck and the spherical bubble both collapse at the same time, and you're left with a horn on one side and nothing on the other. And that's what we're going to try to see here. You know, this is up here, but we've lost our screen. Oh, so the screen fell asleep. Oh, I don't have it plugged in. I pulled it out to reopen it. That's right. Good. meanwhile. Yay! No, it's here. Like, encourage Muffin. Reopen it. Yeah. Okay. So it still takes her a minute to kind of like get everything going here again. I don't want to do this too fast, or she might freak out again. Okay. So that one we saw. Here's our next. Okay, now let me just wait a minute here. Let her settle in. You're a good girl. Okay. So we're going to see this degenerate neck pinch happen here, and it's exactly the same in Ricci flow, in mean curvature flow, but in mean curvature flow it happens for a surface in space. And let's see if it will work this time. Good girl. You can do it. I know you can. Yes, you've been working very hard for me, but they're all loving your beautiful moves. Now, see there, it's almost singular, but it pulls through. And there's no singularity. Okay. So, that's where there's no singularity at all. And now, in this case where everything is exactly balanced, we will pinch a neck and have nothing left on the other side, and you'll just see the one horn. Okay, you're a really good girl. Make it through this, and you're great. Here we go. Good. Oh, beautiful. You're doing so well. I know you can do this. Yes, yes, yes. Yes. Now see the neck pinch down, and little spherical bubble gets smaller, and they're just perfectly balanced, and there, you're left with a cusp. Okay, now confession, I cheated a little bit here. The first movie of the neck pinch, I was very careful and computed everything numerically, including the isometric embedding. For these degenerate neck pinches, I was having trouble finding the right boundary conditions to make it run in the PDE formats I can do in Mathematica. So this is artist conception. So now, you know, like in Southern California, you'll see these ads for, you know, beautiful house just minutes from the beach. And so you picture the beautiful house, and you picture the beautiful beach, and then there's a little asterisk. And it said, 60 minutes by car at 60 miles an hour. Okay. So, but this is exactly what it will look like if you have an honest movie. Just maybe, you know, a little bit different. But it's more important that you get the idea. So now we get into what happens if I do the blow-up analysis on this degenerate neck pinch. Well, let's go back to just a second before this neck pinches, and you see this region here. This actually looks like a rotationally symmetric soliton. It's moving by a diffeomorphism, which is that almost all the motion is this thing shrinking in. And that's because the first singularity was a type 1, where the curvature times the time to the apocalypse, I call it when it gets singular, is finite. And this is where the curvature times the time to the apocalypse, the singularity, is infinite. And when you do the blow up in the first case, you get a shrinking soliton usually. If you blow up around the maximum curvature, you actually get a shrinking soliton. If you blow up around the maximum curvature in the degenerate neck pinch, you get a steady soliton. Okay. So that's then very useful in the analysis, because the idea is to do surgery. So now, even though knowing that the general topology, the Ricci flow can't converge on every three manifold, it has to break up into pieces. Nonetheless, as we saw, you can pinch off a spherical bubble, and that means you've created a piece you don't need. There's no topological reason, it's just an extra superfluous sphere that's going to go away anyway. So here, the surgery is not topological surgery to handle the topology. The surgery is geometric surgery, which we need to handle the analysis. The function of the surgery is to control the curvature. So the idea is, my dad was a real surgeon in Cincinnati, and his favorite operation was appendectomy. So the appendix is this little thing hanging out in your intestine, and it doesn't do anything that we know of except to get inflamed and cause a lot of problems. And he said that appendectomy was his favorite operation because it's easy to diagnose. You punch the person at McBurney's point, and they go, ah! Then they have acute appendicitis, and you want to operate. And the idea is that you want to operate before it ruptures, that is, before it gets singular. And you want to cut the patient open, go in there, cut the inflamed part out, and sew the rest up. And if you don't operate, the guy dies horribly in 3 days. And if you operate, he's back on the street, back at his job in 3 days. And he's just missing something he'll never miss. So here again, the surgery that we do is we go in when we see a neck like this, and now we want to cut this part out. I can make it a little sharper here. I want to cut this part out here to cut off this end where the curvature is real big and paste it together back out here in such a way the curvature will be less. And so now the idea is whenever the maximum curvature gets up to a certain level, Wykład calls it the trigger curvature, it triggers an operation. The patient, the flow in this case, goes in the hospital, and they would cut out all the big curvature region and reduce the biggest maximum curvature by half. Then we put the patient back out on the street, we start running the flow again, and see if he needs another operation or if he gets well. Okay, that's the theory. And so this is done not to control the topology, but to control the analysis. Okay, so now, okay, time's getting late. So in a general topological surgery, what you do is you can replace one sphere across a ball with a ball across a sphere with a change in dimension. And in the case of a neck pitch surgery, what we're doing is we're replacing an S2 cross B1, that's a cylinder, with a B3 cross S0. S0 is 2 points, so that's 2 balls. So you take this cylinder, you cut it open, and you stick 2 balls on. Okay. So that would be a regular surgery, but the kind of surgery I want to do is this appendectomy, where I'm just going to be cutting it apart where I have a sphere, and on one side it bounds a ball, and I forget that, and I kind of sew in a different ball. So now, how can I always do that? Well, the topologists have long understood in a 3-manifold that there's this decomposition along, and this essential sphere is one that doesn't bound a ball on either side. And if every sphere bounds a ball on one side or the other, you call it aspherical. If it bounds the ball on both sides, it's S3, you're done. Okay? So we assume that we have an aspherical 3-manifold that's not S3, and then every time we find a sphere, it's got a ball on one side, throw that away, and then kind of cut and paste a different ball in that has at most half the curvature in the first case. That's our appendectomy procedure. And then, if you want to be really good about it, it's good to patch in this rotationally symmetric soliton that Robert Bryant found. It's the blow-up limit in the degenerate neck pinch. And that helps with, say, preserving a special inequality called the Lee-Yow inequality. So a surgered solution to the Ricci flow is one where you run the flow. When the curvature hits a certain trigger level, you operate, reduce the curvature, run the flow again. If it gets back up to that trigger level, you stop, do the operation, and then run the flow again. And so you get a collection of solutions to the Ricci flow on adjacent time intervals, where the flow at the end of one time interval differs, the metric at the end of one time interval differs from the metric at the beginning of the next time interval, just by one of these appendectomy surgeries. There may be several appendectomies to take out all the bad curvature region. And now we have the following existence theorem due to Perelman, which says that for any time capital T, you can find a curvature level m, the trigger curvature, a number n, and a time interval delta t, and a certain precision, epsilon k and l, which means that you're going to only do surgery on necks where k derivatives are within epsilon of the cylinder on a region which, scaled by curvature, has length L. Okay? So given any aspherical compact 3-manifold in any initial metric with sectional curvatures bounded by 1, just to be nice to start with, an injectivity radius, at least 1 to start with. This went backwards, sorry. Either M is diffeomorphic to a sphere or a quotient of the sphere, or there exists a surgered solution to the Ricci flow up to time t, surgered by epsilon k L appendectomies, as appendectomies of that precision, such that each surgery time occurs when the maximum curvature first reaches M. There are no more than n surgeries, and there's a certain time interval between each of them. And all of these are done in a canonical way. So we have very tight control over this procedure analytically. Well, if you say want to handle the most important cases, which is when the fundamental group pi1 is finite, there's a finite extinction result, and we now have two different versions of this. One by Coley and Minikowski, and one that was done by Perelman, and a lot more details filled in by Morgan and Tian. Coley and Minikowski are world-renowned experts in minimal surface theory, and both these approaches sound very plausible at the beginning, but involve considerable technical details in the minimal surface theory. So the theorem is, on any aspherical compact manifold M3 of dimension 3, with your initial metric controlled in terms of the curvature and the injectivity radius, that's backwards again, and diameter no more than d, and with finite fundamental group, then you have this time t such that any surgered solution to the Ricci flow, where it doesn't matter much how you do your surgery as long as it decreases distance, that there's going to be guaranteed nothing left by the time you get to time t, which means you kept throwing away spheres and ended up with nothing. Okay? Well, you throw away spheres or quotients of spheres. And so that guarantees then that what you end up with is nothing, and what you started with then has to be all the stuff you threw away. So you show that any compact manifold M of dimension 3 with finite fundamental group is diffeomorphic to a connected sum of spherical space forms, quotient of the 3 sphere, and 3 tori, which are S2s cross S1s. So that's a very beautiful result. Now, I don't have time to show you the estimates. So, you saw the fun part. It's kind of like if you were taking a tour of an airplane, a flight attendant would take you you around and show you the pretty seats and the nice food they're going to serve. If you talk to the pilot, they take you up in the cockpit and show all the neat instruments. If you talk to the mechanic, you'd see all the estimates. And you'd see and open up the engine. So you haven't seen all the machinery of nonlinear parabolic partial differential equations that makes this work. But I don't want you to think it's not there. In a plane, you want to think about the engine. It's what's going to actually get it off the ground. So thank you very much, and it was a pleasure being here.
Is there any chance that we can learn something about four manifolds using Ricci flow? Something we don't know yet.
How nice of you to ask. Of course, I've been thinking about that for quite a while. I think I'm actually rather hopeful. The first thing is, in 4 dimensions, there's an extra surgery you can do. That in 3 dimensions, we have just basically this neck pinch, which, like, you kind of take an S2 cross S1, and it pinches down into S2 and breaks into 2 pieces. In a 4-dimensional manifold, you could imagine a S2s over a sheet. You have a sheet of S2s where the one in the middle is smaller than the ones all around the outside. And that middle sphere shrinks down and then pops a hole that opens up. So you've kind of taken out an S2 cross B2 and replaced it with a B3 cross S1. That's a whole bunch of surgery. Now, but you can't do the higher surgeries, which means that there's no surgery you can do and undo. And that's what gives you really good hope that you'll be able to understand topologically what you're left with when you're done. The next question is, can we handle the analysis in a similar way? And the question there is, can we be pinched down to a region that is at least non-negative Ricci curvature, which now is not preserved in 4 dimensions, but it might be you're pinched towards non-negative Ricci curvature plus something else. And you need enough more to prove this Li-Yao inequality. And you might need to impose a curvature condition. Like, you might get a result that classifies 4 manifolds with positive scalar curvature, or something like that. We do know nice conditions that tell you that it's a sphere. That involves looking at the ODE in 4 dimensions. The nice thing there is that you have to understand the Lie group SO4. But SO4 is just 2 copies of SO3, and SO3 is just a cross product. So if you know the cross product, you can do Lie algebra on SO4. I did that already way back when I did positive curvature operator or positive isotropic curvature of 4 manifolds. These are somewhat exotic geometric conditions. But I proved a surgery, a neck pinch type surgery for 4 manifolds with positive isotropic curvature back around 98, 99. Before Perelman stuff came out, and I outlined the whole surgical procedure there. So I'm very hopeful about 4 manifolds, but there's a lot of work to do.
Bitmap using within the open geometries of the texture, how it works in case of so many dimensions, because as I understand the Ricci is a little more advanced as for example Mr. Brown also feel the texture, within the texture
Sorry, I'm having a little trouble hearing the question.
If you
would you simplify, or are you able to say briefly the few words in case of the textures, open GL, for example, GL texture function and bitmaps to your construction to this kind of graphical within the computer science construction? Are you able to say something textures and this Ricci flow?
The texture?
I'm not sure if this is on the subject of the topic, so.
Well, maybe I'll talk to you after.
Right.
A related question to what my neighbor asked. The classical, I mean, in higher dimension conjecture is consequence of H-covariance theorem. So, is there any version of H-covariance theorem in dimension 3? Well, of course, then it's not simply connected version, so you can have Wykład group and things like that. But still, you can ask this question. Do you have an H-covariance theorem in dimension for three-dimensional manifold?
H-covariance theorem,
or just the Poincare conjecture?
Okay, so actually when I was a grad student at Princeton, I heard Milner lecture on the proof of the H-covariance theorem. And now that was like back in like 64, 65, so I'm trying to dig this up from my memory. So the H-covariance says something about you have 2 3-manifolds that are the boundary of a 4-manifold. And
inclusion is a homotopy equivalence, and inclusion is a homotopy equivalence of one component of the boundary. And since it's not simply connected, so there is some additional invariant which vanishes. And then the conclusion is that this is trivial, so it's a product of this one manifold by.
So I guess I could start with a covariance. It gives me a 4-manifold with boundary. And I could do something like I could fix the metric on the boundaries and then run the Ricci flow on the interior with the given boundary conditions and then see what it does. That's interesting. The first thing that would happen is that you would still have all the same problems of singularities for me because you wouldn't know anything in the region in the 4-manifold that really was local. And it's very hard in PDE to use global information. Yes, you might get it out of some integral quantity, but I don't immediately see that. So you'd have to be able to handle the singularity analysis. If I knew how to handle the singularity analysis, then I could probably do things on 4-manifolds. And if I could do things on 4-manifolds, then I'd be ready to tackle 4-manifolds with boundary and try to do an H-covariance. So that's a lovely suggestion. I'll file it back in my memory. The answer is, I hope if I'm back here in 20 years, maybe I'll be lecturing on it.
Well, there'll be a part of profound dissection. What do you think, which part of physics may use your mathematics?
Well, now that's another thing I have in mind. That we now have the Ricci flow proving interesting theorems in geometry and topology. So it would be very nice if it also proved important results in algebra and physics. In algebra, that's not so far-fetched at all because you can look at the Ricci flow on Euler metrics. And if the initial metric's Euler, it stays Euler. And this has been much studied. My friend Zhao Huaidong did it back in the 80s, where there's a special case where you have a canonical metric, where the Ricci tensor is homotopic to the Euler form. The Ricci, the Chern form is a multiple of the Euler form. So in that case, he proved that the solution exists until the volume goes to zero in a finite time. And Perelman actually has worked on that problem too, and proved that the solution exists until the diameter goes to zero. So I know quite a lot about this. It's gotten a lot of study. I don't quite know what algebraic problem it would solve. But in the physics case, I do have an idea in mind, which is that you can run the Ricci flow on a Lorentz metric. Now, the problem is a Lorentz metric has a negative sign, and that would be doing a backwards parabolic in that time direction. And that isn't going to work. But there's a special case that does work, which is if you have a stationary solution. That is, if you have a Lorentzian metric with a time-like filling vector field. Then, when you run the Ricci flow, the directions in which it wouldn't work drop out. And that means that you get a nice parabolic flow, basically on the quotient. So you can look for stationary Lorentz metrics solving Einstein's equation. And there's an interesting generalization. Say if you want to add electromagnetism, there's your classic Kaluza-Klein theory, where you add one more dimension for the electromagnetic field. And the more dimensions you have, the more possibilities for interesting solutions. And now if you have extra symmetries, like say a rotational symmetry around an axis, then that reduces the essential number of dimensions, and the problem gets more tractable. So what I'd love to do is to use the Ricci flow to find Einstein metrics and Kaluza-Klein metrics that might even have something to do with string theory. Okay. Ambitious? Yeah, sure. Chance of success? If you say 1 in 1,000, I'll be happy. I didn't put it that high when I started on the Poincare conjecture. But I'd rather be racking my brain over something worth doing, because I get stuck just as quick on something trivial.